Alright, this is the practice test. Which of the following has the highest boiling point? So boiling points are defined by the types of intermolecular forces that govern a particular substance. And remember that there are intermolecular forces that include London dispersion forces, which just depend on how many atoms are in a particular substance, because it depends on how many electrons there are. There are dipole-dipole forces that occur in polar things, and then there's a special case of dipole-dipole forces called hydrogen bonds. And hydrogen bonds occurs between atoms that have hydrogen connected to an FO or an N, a phone. And those are special because FO and N on the periodic table are very electronegative, and so they pull hydrogen's electron really close to itself, exposing hydrogen's neutral nucleus, and then they have a hydrogen interaction between one molecule and another. And so if you look through these, you see two of them that have an H connected to an FO or N right here. And so if you draw the drawn out structure of this, we have 1, 2, 3, 4, 5 carbons in a row, and then we have an H connected to FO or N. And then in this one, you can see it's drawn just a little bit differently. So we have C, and then we have these two CH3s coming off of that carbon. And then we have a C, and then we have an OH off of there. You'll also notice that this has 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. And so they're the same molecule, they're just different organizations of themselves. And so they both have a hydrogen bonding, which makes them be the best sticker-togetherers of each other. So if there's another one, I won't draw the whole molecule right here, but this hydrogen would connect to this oxygen right here. And this hydrogen right here would be connected to this oxygen right here in a weak intermolecular force called a hydrogen interaction or a hydrogen bond. Same thing would happen with this one. So since they both have hydrogen bonds, that's equal. The next thing to decide then is the London dispersion forces that both of them have. And since both of them have the same number of carbons and the same number of oxygens and the same number of hydrogens, we assume that they have equal number of electrons. Because remember, London dispersion forces depend on the number of electrons. Well, if all things are equal, then in London dispersion forces, it comes down to surface area. The more surface area something has, the more connectivities that it can have. And since this is a long hot dog shaped one right here, it's going to have the most surface area versus this one that's kind of circular shaped here on one end. And so this one right here is going to have your highest boiling point. It's going to stick together the best because, first of all, it has hydrogen bonding, which this one does too. Second of all, it has London dispersion forces that are equal to this one, but this one's got more surface area, therefore it's going to stick together better. Number 2, the stronger the two primary forces responsible for binding ethanol molecules to one another in the liquid phase. Well, ethanol is C2, and then there's an OH connected to the end right here. So this is an alcohol. That's why it ends in OL right here. And alcohol is an OH on the end of it, or somewhere in the molecule. And since this has an OH right here, it's going to have hydrogen bonding characteristics. And so if it sees, when it sees another ethanol molecule like this O is going to be attracted to this H right here of another ethanol molecule. And these by far are the strongest of the types of intermolecular forces, with all things being equal, unless there's millions and millions of electrons, which really big, huge, large molecules would have. But these aren't really big, huge, large molecules, and they do have hydrogen bonding, and so letter B is correct. That is the primary force. Now, they do have London dispersion forces too, but they're not as strong as the hydrogen bonding forces, which are probably 10 to 20 times as strong as London dispersion forces until you get to really giant molecules. Number 3, which of the following cannot participate in hydrogen bonding? Well, remember, you have to have an H connected to an F or N. Here we have an H connected to an FNORN. Here we have an H connected to an FORN. Here we have an H connected to an FNORN. And once again, an H connected to an FORN. And so C is the only one that cannot participate in the hydrogen bond. Number 4, based on the figure above, the boiling point of ethanol under the external pressure of 454 is, so the first thing that we want to do is find where 450 torr is. So that's right about, or this is going to be about 500 right here. So 450 is going to be right here in the middle. And then we want to follow it over until it hits ethanol, which is right about here. And then we want to find the boiling point, so we're going to drop it down here and find out where it crosses the x-axis. So it looks like it's a little shy of 70 degrees, but which one is closest? So 70 degrees, we're pretty close. My line might be a little bit crooked. Bonus, what does a point below and on and above the curves tell you about the state of the substance? So if we're below here, we're in the liquid phase. If we're above here, that means that we've already boiled and we've gone into the gaseous phase. So that's what it would tell you. Number 5, which of the following is a covalent network solid? So there are 4 different kinds of solids that we learned about. There are ionic, molecular, covalent network, and metallic. So ionic things have positive and negatively charged particles inside them, and they usually have a metal, which is over here on the periodic table, and a non-metal in them. Now, it could be a metal and a polyatomic ion. That's very, very common as well. But they're super strong interactions. They usually have really high boiling points and melting points because this positive-negative electrostatic interaction sticks them together. Think of things like NaCl, like K3PO4. Those would be a metal and a non-metal, a metal and a or a metal and a polyatomic ion. The more charge it has, like this one has a -3 charge and this one has a +1, the better they're going to stick together. All right, molecular solids are made of only nonmetals. Think of these as things like sugar or things like ethyl alcohol that we just talked about. They're going to have only these kinds of things in them right here. They usually have lower boiling points, lower melting points, lower than what ionic things do. The things that hold these together are the intermolecular forces like London dispersion forces, dipole-dipole forces, and hydrogen bonding forces, and those are not nearly as strong as the interaction between ions like these guys. Covalent network solids, this is on page 503 of your digital text. This is the 13th edition. Usually contain the nonmetals, carbon, silicon, and maybe the adjacent atoms like germanium, phosphorus, nitrogen, boron. Those nonmetals or metalloids right there are involved in covalent network solids. They consist of atoms held together in large networks by covalent bonds. Because covalent bonds are much stronger than these types of interactions like London dispersion forces, dipole-dipole forces, and hydrogen bondings, they usually have really, really high melting points. Examples are diamond and graphite of just carbon-containing substances. 2 of the most familiar covalent network solids are things made of silicon and germanium and quartz. Silicon carbide and boron nitride are all other examples of that. Here is diamond right here, and then here is graphite, 2 allotropes of carbon that are examples of covalent network solids. So knowing that background knowledge, which is a covalent network solid, well, silicon dioxide would be, diamond also would be, and so more than one of the above is a possible answer. Metallic solids, since I didn't finish this part right here, are made up of metals, and so those are ones that hold like copper together or aluminum together, or an alloy of 2 of them mixed together. The force of attraction that exists between dissolved ions such as Na and the solvent water molecules are called ion-dipole interactions. And so if we have water here, water of course has a dipole moment where there's more of a positive charge, more of a negative charge here like this. And then we have an ion of maybe like Na+. So the sodium ion and the water molecule right here would be attracted to one another. This would be an ion-dipole interaction, letter D. That's what helps things dissolve lots of times that are ionic. Number 7, for gases in solution, solubility decreases as the temperature increases. They're inversely proportional to one another. Number 8 and 9 refer to this diagram right here. And so number 7 says, number 8 says, a sample of carbon dioxide gas at temperature and pressure conditions of 10 atmospheres and 15 degrees Celsius. The pressure is decreased at a constant temperature. What happens? So pick approximately 10 atmospheres. Notice it goes from 5 to 73, so the scale isn't super good. Anyway, follow that over to 15 degrees Celsius. So this is 31, and this is negative 56, so 0 is probably somewhere in here, so this is probably 15 somewhere in here. So follow these over right here, see where it crosses this line, drop that down to 15 right about here. Okay, and so the pressure is decreased at constant temperature. What happens? So we're somewhere in here in the liquid phase, and then what we're doing is we're crossing this line and become a gaseous phase. So at sufficiently low pressure, so as we lower this pressure right here, this liquid starts to change into a gas. And so letter C, the liquid starts to go to a gas. Number 9, the last one for this video, says, which of the following temperature and pressure conditions describe the sample of carbon dioxide in the supercritical phase? So the supercritical fluid state would be up here above the critical point. That's what C stands for here. And above the critical point, no amount of pressure can change it from a gas back to the liquid phase. And so sometimes you'll see a horizontal line right here, just indicating that you're above the critical point. And so in this case, we'd be in letter C right here, 40 degrees Celsius, so somewhere up here. And we'd be at 75 atmospheres, so we'd be above this 73, so we'd be like up over here somewhere. That would be the critical phase. That ends this one. Continued on the next.